Okay, so let me say a couple of words like the next homework. So this is what you get for asking questions in class. So if you remember, we showed that you have a PID if and only if it's a UFD in every. So in every the GCD is a linear combination. So I thought about this and generalized it a little bit. Show that you have a principal ideal domain if and only if you're a Bezier atomic domain. So what does a Bezier mean? It means that every finitely generated ideal is principal, and atomic means that every non-zero non-unit is a product of irreducibles. So Bezier is sort of like principal ideal domain, except maybe some of the ideals aren't finitely generated. If you throw atomic into that, it forces all the ideals to be finitely generated, which is kind of cool. Two is kind of a generalization of a classic, if you will. Let R be an integral domain. In part A, show if X and Y are non-zero elements and the least common multiple of these two elements exists, then the greatest common divisor of these two elements exists. So least common multiple in a certain sense is to say the two things have a least common multiple is a stronger statement than to say they've got a greatest common divisor. And to follow up on that, show that it's possible for the GCD of two elements to exist and have the least common multiple not exist. See if you can get me in this. For the remainder of this problem, you need to assume, well, you often need to assume that R is a GCD domain. What a shocking definition this is. That means that any two non-zero elements has a GCD. And my notation, all these things are non-zero. Show that if you multiply A times the GCD of XY, it's the GCD of AXAY, right? And by the way, this kind of builds to a crescendo. I put these sort of in because I think you can kind of build the puzzle and use them along the way. Show that if GCD XA and GCD of XB is 1, by the way, what do I mean by that? This notation, when I said the GCD is 1, that means that their only common divisors are units. Okay, that means then the GCD of X and AB is 1. You do need GCD domain for this because it is possible if you're not in a GCD domain for two things to have GCDs 1 and then their product picks up a factor. Show that if the GCD of XY is 1, then and X divides AY, then X must divide A. And finally, show that if R is a GCD domain, then the least common multiple of any two elements exists. So your counterexample better not be the GCD domain. And finally, with respect to the spirit of sort of the number theory and basic stuff that we're going to be talking about quadratic reciprocity, this is Fermat's accomplishable equation, right? And everybody knows some Pythagorean triplets, right? And forget the silly ones like, x squared plus 0 is x squared. Everybody knows the interesting ones. 3 squared plus 4 squared is 5 squared, 5 squared plus 12 squared is 13 squared, et cetera, et cetera. Find them all, parameterize it. And let me give you a hint on that one. So I want you to parameterize for the solutions in the integers. So here, I'll get this screen out of the way so I can give you a little hint here. Turn it off. So here's my hint. First, consider this by dividing by, okay, Quasimodo. Okay, so first divide by z squared, if you will, and look at rationals. So look at the circle x squared plus y squared is 1. So try to parameterize a line going through this, right? So, what do you want? You might want rational slope. You want this to intersect a rational point. See if you can use this to kind of dig out a parameterization of all the solutions. It's kind of a fun problem. And, actually, you should get something that looks familiar if you've ever taught Calc 2. In fact, how many of you know what the Weierstrauss substitution is? Oh, good. I get to do calculus and 9,000 bucks. So I can't believe I'm doing this again, but it's so fun. I love this. So I know how to do that. Yeah, good luck with all that, right? That's awful. This is actually a connection to this homework problem. You might see some stuff here. Is everybody on board with me about this is a tough interval to do, right? I mean, it's obvious that you might say, well, let's u equal cosine theta, so that's your du part, but then what are you gonna do about that? That's a bit of a mess, right? I just think, I guess Weierstrauss was one of those powdered wig guys that had too much time on his hands. This is like really clever. The substitution for this there's your substitution that will always work. T equals tangent theta over 2. How many of you have ever seen this before? Well, you should sign up for it. Why does this work? Well, let me draw a picture for this. T over 1 is the tangent of theta over 2. Agree? So the missing side should be doesn't look like it's helping us so far. But here's the deal. What do we want to do? We want to take care of sine theta and cosine theta, right? And so I don't know much, but I know that sine of theta is equal to 2 sine theta over 2 cosine theta over 2. Correct? Which here you can read off the triangle. Sine of theta over 2 is t over radical 1 plus t squared. And cosine theta over 2 is 1 over 1 plus t squared, which is 2t over 1 plus t squared. Miraculously, the radical disappears. All right. And cosine theta is cosine squared theta over 2 minus sine squared theta over 2. And so you can do basically the same thing here. The cosine of theta over 2 is right 1 square root of 1 plus t squared. So we've got that. And finally, of course, I do need to deal with this d theta business. This is going to be secant squared theta over 2 times 1/2 theta. If I still remember how to take a derivative. Okay. And what is this? This is tangent squared theta over 2 plus 1. Right. So this is 1/2. Let's see, what's tangent squared theta? So in summary, here's what I have. D theta is 2 dt over 1 plus t squared. Sine theta is 2t over 1 plus t squared. And cosine theta is 1 minus t squared over 1 plus t squared. So the upshot of this observation is when you have quotients of sines and cosines, and in fact any trig function, you can turn them into quotients of polynomials, right? So this will always work in the sense that it always turns a quotient of trig functions into a quotient of polynomials, which in theory you can solve if you know what the roots are just by doing partial fractions. So this always turns quotients of trigs into quotients of this. And these relations might look familiar as you work through your problem. By the way, just for giggles, you might, there's also a way that you can do it with the hyperbolic trigs as well. Okay, any questions on that? All right. So never thought you'd do calculus today, right? Okay, so the last thing we were talking about was the Legendre symbol. And the last thing I gave you was theorem 416, which kind of tied together some of the stuff. Let me make sure I've got my rules set up here. I want one Legendre symbol A mod P is A P minus 1, 2 mod P, 2. The Legendre, excuse me, the Legendre symbol is multiplicative. And that's even true if either A or B is equal to 0 mod P. And finally, if A is equivalent to B mod P, then symbol AP. We've already sort of covered 2 and 3. I think the only one that that we've really kind of left twisted in the wind a little bit is the first one. Can somebody discern why that's true? Why is the first one true?
Because you're looking for squares mod P, and so if squares congruent to one thing mod P and the two things are congruent to each other.
Okay. Right, that's so let's do the proof one. Let's suppose first A is a square mod P. That is to say that AP is 1. Well, there exists an X mod P such that, well, actually, let me do it this way. Let X generate so suppose that this is a coset mod P of generator of the multiplicative group. What can you say about the relation between X and A? Well, it must be true that X to some even power So let's just take this to the p minus 1/2 power. X to the 2n, p minus 1/2 from the a to the p minus 1/2 mod p. But then, on the other hand, this is x, the p minus 1 n mod. But the giveaway here is, since x is a generator of the non-zero elements of Z mod p, x is not equivalent to 0 mod p. So in particular, x to the p minus 1 is equivalent to 1 mod p. So we've shown that in this case, when a is a square, then this is the same thing as a to the p minus 1/2 mod p. The proof when it's not a square is similar. So exercise. That's very similar to this. Okay. Let me give you a corollary to this. 417. And this one's kind of really nifty here. So if you look at minus 1 mod p, this one's kind of a big. So this actually comes up in number theory. What is this symbol telling us? This symbol is trying to tell us whether or not minus 1 is actually a square mod p. Of course, 1 is a square mod any prime. When is minus 1? When does your mod p have an I? Well, this is minus 1 p minus 1/2. Mod p. Doesn't matter in this case because we're just seeing ones. So minus 1 is a square mod p. Mod not prime p. Does anybody see the condition? That's right, because your big concern is this hinges on whether p minus 1/2 is even or odd. Right, if this is odd, the symbol gives you -1. That is, if the exponent is odd, and the symbol gives you -1. And if the exponent is even, it gives you +1. What do you need for this to be +1? You need this to be even, so you need p minus 1 to be a multiple of 4. Right, okay. So in other words, so for example, minus 1 minus 1 is a square mod, for example, 5, 13, 17, 29, etc. Minus 1 is not a square mod 3, 7, 11, 19. Right. So that's another example, you know. I think philosophically speaking, I think it's just terrible. They call I like an imaginary number because then, you know, all the people that watch flat earth videos think that these things don't really exist and so forth. This is, first of all, philosophically speaking, I believe in I because I can build it right here on this board. Right. When you start talking about square root of 2, I can build square root of 2 too. When you start talking to me about pi and e, that's a little bit more flaky actually. And in fact, I like this because if you ever want the square root of -1, just look at mod 5 and there it is, right? Square 2 and you get -1. So let me give you, so here's kind of the big exciting theorem here. And I'll give you kind of an application. Theorem 418. Some people call this whole mess quadratic reciprocity. Let P and Q be odd powers. So they're both odd and they're distinct. Number one, so we've already talked about this one a little bit. The Legendre symbol on -1 is -1 to the P -1 over 2, which is equal to 1 if P is equal to 1 mod 4, and -1 if P is equivalent to 3 mod 4. Notice that, of course, every prime, with the exception of 2, is either equivalent to 1 or to 3 mod 4, because all the other ones, all the 2 other cosets only contain even numbers. 2 is a little problematic, and we've got to deal with that. Anybody know what this one is? Just for fun. This one's also kind of a power of -1. What's that? No, not quite, but you're sort of right, because it does depend actually on an 8, and we're gonna see that in the frame. Yeah, oh, but yeah, in the conclusion like this, it's going to it's important mod 8. So yes. So there's your 8 right there. Yeah. So this is equal to 1 if P is equivalent to 1 or 7 mod 8, and -1 if P is equivalent to 3 or 5 mod 8. So for example, let's say mod mod 47, 2 should be a square. Right, because if you look at 47, that is equivalent to 7 mod 8. So there should be something that squares to 2 mod 47. Yeah. Yeah, that's right. In fact, 7 squared That one was kind of easy, I guess. Sometimes they're a little harder to find. Let me ask you this, 2 is a square, what about -2? Is -2 a square? -2 is not a square, because 2 is a square, right? For negative, so for -2 to be a square, what would have to happen? -1 would also have to be a square. That's your only hope, right? So. If you look at, if you look here, 47 is not, actually 47 is equivalent to 3 mod 4. So, -1's not a square here. On the other hand, if you look mod, let's do something more exciting than that. If you look mod 11, 2 is not a square. Right, because 11 is equivalent to 3 mod 8, so 2 is not a square. And neither is -1, because 11 is equivalent to 3 mod 4, right? So -2 must be. Right, because 2 is a non-square, -1's a non-square, so the product has to be a square. And of course, -2. And there you go. 3 squares to -2. And finally, I haven't even finished, I'm so excited about this, I'm starting to do the down for me. There, 3. This is like a galactic miracle on order of fundamental theorem of calculus, I think. If you look at PQQP, this is -1, P -1 over 2 times Q -1. Or in other words, QP, another way to write this, is equivalent to -1 to the P -1 over 2, Q -1 over 2, Q. Because notice when you multiply any one of these symbols by itself, you're always going to get 1, right? This is, I find this incredibly miraculous, that the status of Q being a square mod the prime P is intimately related to the status of P being a prime mod Q. To me, that's, there's no good reason for that to happen, but it does. Let's do a couple of examples. Let's do. I'm going to do what? So let's evaluate this symbol here. This is 20. So really what this is asking, I'm evaluating the symbol. I'm going to get a +1 or -1 when I'm finally done with it. And really what's being asked here is 20 a square mod 131, right? Now, of course, you can go through with your calculator or whatever, just going through and testing things. Nobody wants to do this crap, right? It's awful, right? So what is reciprocity or in the properties of the symbol? Let's do. This is 4. One of the properties of the symbol. Break that up. Okay, so what should I shortcut now? This thing is always one, agreed? So I can make this go away because this is always a square. So where we're at here is 5, 131. Now, this, prime on top, prime on bottom, so here I want to apply quadratic reciprocity. And this should be 131, 5 minus 1, 5 minus 1 over 2 times 131 minus 1 over 2. See, of course, let me point out that, of course, both of these things in the product up here have to be integers, right? And that one's even, right? So this is, right, because this is going to be an even power, -1, agreed? And now what? Reduce it mod 5. Right, because 131 is equivalent to 1 mod 5. So the answer is yes, 20 is a square mod 131, just like that. Here's one with my, here's one with my former favorite prime. I found an improvement over this one. The better prime is 8675311. Because actually, not only is that prime part of prime twin. Okay, so first move, what do you think? Well, let's do this actually. How about? Um, 56, right? And why did I do this? Because this one's going to disappear. Right. Okay, so I kind of see what's going. Yes,
Why did that one disappear?
because 4 is always a square about anything.
Oh, okay, yeah, I'm good.
That's 2. What a shocker. That's 2. So we'll use the part 2 of the previous one. And this one, we're going to straight up use quadratic reciprocity. So let's do this one at a time. So really, the big question is what's this equivalent to mod A? Well, so 300 is, yeah, I think it's 5 mod A, isn't it? Yeah, because you can forget about all this. You can forget about all this because any 1,000 is divisible by 8, right? So you can ask yourself the other question: what's 309 mod 8? Right? That's kind of a shortcut to that. And if I divide that by 8, I get 30. Let's see, that's what. Yeah, so 69, 862. Yeah, it's 5 mod 8. So 8675309. So what does this thing become? This is -1, isn't it? So this is minus 7. Now, I guess I've got to bother to figure out what 8675309 is mod 7, right? Well, no, I'll do that in a minute. I'll go ahead and do quadratic reciprocity. So these are both primes, right? I haven't proved this for you, but it is. And this is negative. -1. And 867. 9 minus 1 over 2 as well. Now, what do you know about this one? This one's even. So at the end of the day, this piece is gone. And so let me just figure out what this is, mod 7, so that I don't waste too much time. Right out of this. See if you guys get what I guess. 6, I guess. Yes, I got 6. You guys will get 6 months there. So this is now, I guess at this point, 7's small enough for us to figure it out, but you could go reciprocity further if you wanted to. And maybe we'll do this just for dramatic purposes. This actually should be 6 should be a non-square, so my answer probably shouldn't be 1. 2, 7, 3, 7. Right, and let's see, 2, 7. That's a +1, isn't it?
6 is also -1.
Oh, that's a good observation too, right? There's gonna be a lot of ways to skin these cats. He's right. 6 is -1, so that's a good way to do it. This is going to be -3, 7. Reciprocity again. 7, 3, and this one's fun because this is 7 minus 1 over 2 times 3 minus 1 over 2. And these are both odd. That's a 3 and that's a 1. So this is going to be minus times minus is plus. So it's 7, 3, which is 1, 3, which is. Okay, any questions?
What number actually squares the 56?
That's the kind of thing I give to a graduate student. Let's see. Okay. Okay, any questions? So you can have lots of fun. Oh, I was gonna give you one other application. Or this is really more of a why do I care sort of thing. Or why would I ever want to use this? Well, it turns out, and we're gonna maybe get into these weeds later, but theorem.
255,350. Okay.
I was thinking that too. I was like, I don't know.
Yeah, did you get that off of Wolfram or something
Yeah.
like that? Okay. Here's a theorem by Gauss. I think it's by Gauss anyway. But it's classical in that sense. It goes way back. P is the sum of two squares. So that is, I can express a prime number as the sum of two squares if and only if. Anybody know what this is?
It's like P prime, like we're assuming P is prime.
Oh, thank you. If and only if P equals two. Oh, P equals 1. Yeah, you get that degenerate two case, but besides that, it's feasible. And this is equivalent to saying P is the sum of two squares. If and only if minus 1 is a square. On P. Because, of course, we've just seen from what we know about the Legendre symbol that that's what it means for non-prime. And of course, mod 2, 1 and negative 1 are the same thing, so minus 1 is a square mod P. So this symbol is often used as the Legendre symbol can tell you whether a prime splits or not in a quadratic extension, and hopefully we'll get kind of deep into that later, but here's what happens. This is kind of fast and loose, but this is sort of what's going on. By the way, just out of curiosity, what do you all know about Gaussian integers as far as what kind of nice ring it is?
Putting it in.
Okay, yeah, you guys went for the throat. That's exactly right. It's a Euclidean domain, right? And in fact, the standard, the norm is it can be shown that this thing is actually a Euclidean norm, right? Exactly in the definition of the Euclidean domain, this is the phi function that measures size, and you can always divide and get a smaller remainder, right? What does it mean for a prime? So if P in Z is a positive prime, what does it mean for this to be a sum of two squares? Suppose you could write P is equal to A squared plus B squared. Doesn't that mean that in the Gaussian integers, so this question, that sounds like, you're just asking a question about what primes show up as a sum of two squares represented by some quadratic form. Well, when can I write a prime this way? Is asking this question, the ring, when does this prime actually break down? Right? So notice that when you can write prime as a sum of two squares, when that prime lives up here, it loses its status as prime and factors down. If the prime equals 2, or P is equivalent to mod 4, it turns out that if P is equivalent to 3 mod 4, that is, it cannot be written as the sum of two squares, then P remains prime. In the Gaussian. And there's nothing super special about the Gaussian integers. It's an exceptionally nice example because of the fact that it's in fact a principal ideal domain. But take z adjoined with the square root of 2. Take z adjoined with the square root of I radical 2. Take z joined with the square root of -5. Some of these rings aren't as nice, but you get this whole theory about being able to write primes as sums of quadratic forms, and is related to what happens to the primes upstairs. Okay. Yes.
Just kind of a fun fact related to what you had there about how whether things can be written as the sum of squares is related to the Legendre symbol. The term quadratic reciprocity, I'm pretty sure it comes from the proof technique that Euler used to prove this theorem about primes congruent to 1, 1/4, and only if they can be written as the sum of squares, like because he used this technique for all these similar proofs, and there'd be it's kind of like induction. There was a descent step and a reciprocity step, and the reciprocity step is similar to induction, but that's where the term quadratic reciprocity comes from.
So I did not know that. Yeah, so yeah, and actually have any of you, I guess you have you seen a proof by infinite descent? It might be the Fermat's case. Fermat's theorem in the case of equal score is a good example for that one. Okay. So let me kind of collect this here. Using my notation before, so I'm not gonna read all of that. Minus 1p is equivalent to minus 1 to p minus 1 to 2, which is 1 if p is equivalent to 1 on 4, minus 1 if p is equivalent to 3 on 4. Two 2p minus 1 to the p squared minus 1 over 8, which is 1 if p is equal to 1 or 7 by 8. P is equivalent to 3 or 5 by 8. And finally, reciprocity. Okay, so we've kind of gone over the first one quite a bit. So let me look actually at the second one. So I'll get started here. So what I want to do is let okay, so this is the field of P elements, Z mod P, if you will. Well, this is going to be an algebraic closure. This field of P elements again. In this field, let omega be a primitive 8th root of 1. So, Rodrigo, there's your 8 coming up again. So what does this mean? This means that omega to the 8 is equal to 1, right? But omega to the k is not equal to 1 for any k between 1 and 7. So 8 is the smallest positive power of omega, that gives you 1. So let me leave you kind of with this. So I'll let you kind of think about this one. So what do you suppose omega to the 4th is? Well, it has to square to 1, but it can't be 1 itself because that would deny its primitive. So this is -1. And so if I multiply by omega to the -2, I get omega squared plus omega -2 is 0. Let Z omega plus omega inverse. Now, check this for next time. We'll go over this next time. Actually, it's an easy check. It's embarrassing for me to ask it. Z squared equals 2, all right? That's what we'll pick it up next time. It's easy. This is trivial to verify. But we'll pick that up next time. Any questions? Any questions on it? All right. Well, you all have a good one, and I will see you at least by Wednesday.